G'day all, welcome to this week. I should mention, actually I don't know whether I need to mention because you don't know about it, but I did actually record a whole bunch of videos a couple of days ago. Got them back to my office to start uploading them and discovered that the battery on the lapel mic had been low or nearly flat. So the audio was all either fuzzy and distorted or non-existent for the 2.5 hours of video that I just done. So I'm redoing them from scratch. Hopefully they'll be quicker, smoother and better this time than having done them before, because I'll have done a rehearsal. So hopefully that's useful and interesting. So this week we're talking a little bit about assessment in general and instructional models. And I'm going to talk a little bit about a number of issues around assessment. And then next week as well, we'll talk further about assessment. And I will also hope to have interviews with some working teachers, one or two, about the new senior secondary syllabus assessment picture and how it's looking and how we work with that. I do kind of notice that assessment is quite a big piece of the course, probably more than usually, but in this case you're coming in with the content already, and you're doing more of the content-specific pedagogy in the labs/workshops with Ben and Gordon. So what we're doing in the common course content that's for everybody is a lot of it talking about how we prepare our students for assessment. So we'll talk about alignment in a moment. And basically, if we have an alignment between curriculum, pedagogy, and assessment, then essentially by talking about assessment, we're talking about pedagogy and curriculum anyway, that the three things are strongly related to each other. So I hope that kind of explains a little bit why the emphasis is as strong as it is. There are a whole variety of range and issue of topics, but in terms of preparing you to be ready to kind of go out on your placement and then to be ready to go out and be a beginning teacher, preparing you for this new senior secondary system is going to be kind of important. So it's one of the things that I'm trying quite hard to do. So just a little bit really quickly on instructional models. So these are approaches to pedagogy. These are approaches to teaching senior science, and they're sequences. And I'm going to talk through it quite quickly and try not to repeat myself. So we'll see how we go. Basically, we have a repertoire. There isn't a one true model. So what you want as a professional is to have a range of abilities, approaches, ways of working that is appropriate for your purposes, that sets you up well to be able to make the professional judgments about what you do and how you do it. So I'm going to talk quickly through three models, which you'll see some similarities and differences, and then we'll talk about how you might use them. So there are a number of skills that students are developing as part of the process. And we'll talk, I think next week, about the QCAA cognitive verbs. And you'll see a number of these come up in that cognitive verbs list. But these are the kinds of things that students are learning to do. So not just learning to know, not just content that they're memorizing and recalling and comprehending, but content skills that they're learning to exercise. And these learning sequences are designed to help them develop those skills. So the first one's the 5 E's, which you may already be familiar with from your junior secondary curriculum course, or you may have even encountered it at school, I'm not sure. The 5 E's was created by the Australian Academy of Science. Initially, I think it was adapted by them from somebody else. But it was originally used in the primary connections materials for primary science, and then in the learning by doing materials for junior secondary science. But it's quite a useful scheme. Again, it's not inherent in any of our syllabus documents. It's a way of teaching. It's a pedagogy that relates to that curriculum. 5 steps: engage, explore, explain, elaborate, and evaluate. I'll talk through each of those in a little bit of detail in a second. But the point that I want to make here is that although it's a sequence of 5, there are arrows going forward and backward at each of the steps, and there's no sort of preferred starting step or finishing step. There are a range of ways you could use these steps rather than just linearly from 1 to 5. So the engage phase is getting the attention, stimulating their thinking and helping them access their prior knowledge. So there are a range of activities you might do to actually do that. You might do a demonstration experiment or show them something outside the classroom or a whole variety of things like that. You might have them read something, you might have them write about something. What do you know about this? Just write about it. Graphic organizer, KWL, what do we know, what do we want to know, and what have we learned? So that's an activity where you kind of get them to pull together, what do we already know about this topic? What's interesting? What would we like to know? What are our questions and so on? And then what have we learned? And then the final one that we sometimes add to that is an H, which is how we know. So once the students can make a judgment and say, this is what I've learned in this unit, but can they say, and here's my evidence to support the fact that I know that. Here's how I know. Here's the evidence I use to arrive at that position, if that makes sense. So brainstorms, other kinds of activities to engage the students in the concept. The explore phase, working with the concept, working with the ideas, making decisions, doing problem solving, collecting info, and so on. So again, kinds of activities. An investigation, something like the old extended experimental investigation. Reading sources, going to other people's data. Problem solving, model creation, model construction, and so on. So there's a number of activities that we use to elaborate on the concepts and work with them and help the students to develop and enrich and also challenge problems with their existing concept. The explain phase, students typically do the explanation first. So, you know, the explain phase, sometimes beginning teachers go, oh, the explain phase, this is where I explain to the students. And I talked last week about teacher explanations, and teacher explanations are important. But in the 5Es model, the explain initially is the students explaining it to the teacher, to each other, learning to develop an explanation and what an explanation looks like. And then the teacher might help correct, scaffold, support, challenge their explanations to improve the quality. So making arguments as well. So again, I made that distinction between argumentation and explanation, and both of those things come up in this discussion. Teacher explanation does have a role, and activities with thinking skills. So compare and contrast, classify, error analysis. And again, you'll see those terms come up again in the cognitive verbs list, which we'll talk about next week. Elaborate. To elaborate is to, once the students have the concept, get them to work with it, expand it, apply it to the real world. So a number of activities, again, come under this elaborate step. Some of them are ones that you've already seen under the other steps, but these are ways of doing an elaboration. Oh, sorry, let me go back. Ways of extending their knowledge. So if their knowledge was initially relatively simplistic and shallow, it's making it broader, deeper, more powerful, more comprehensive, if that makes sense. And evaluate, the final step, which I slightly disagree with the slide, which I partly borrowed from Harry and then adapted myself. But teacher assessment is part of the evaluation, but the students should also be evaluating their own knowledge. They should be doing that metacognitive activity of, what do I know? And that's where the LH on the KWA LH chart comes in. They need to be able to make judgments about what they know, how much they know, etc. So you can have them to develop the scoring tool, have the students develop a criteria sheet. We'll talk about criteria sheets next week. A performance assessment is an assessment of a skill in the lab. So rather than a paper and pencil exam test of knowledge, a performance assessment might be conduct a titration and show me how that works. Prepare a slide and draw what you see under the microscope, show me how that works, and so on. So they're performing a skill which has both a manual and an intellectual component to it, and then you're assessing their ability to do that. Produce some sort of product, write something, put together a portfolio and argue why the pieces are in it, and so on. So there's a number of ways in which the teacher assesses and evaluates and measures the students' understanding, but also the students evaluate their own learning. There's a range of different question types, and I'm not going to spend much time on this, but it's reminding us of the range of ways in which we can ask questions in the lab. Just a reminder that if I do whip past a slide quickly, you're watching me on video, you have a pause button. So if you want to look at this slide in more detail than I give time for, just pause the thing. It's easy. Okay, so this is another model. So the 5Es was the first model we talked about. This model is from a primary science book from the UK by Loxley, Dawes, Nichols and Dorr. I'm going to say Loxley et al. Because it's a mouthful. And although it's a primary book, it's still a model that's relevant for us and it's useful. So exploration establishes the puzzle or the dilemma. So this is like the engage phase essentially. It's like the engage and explore phases. So it's setting up the question and doing some preliminary investigation. So you can see the parallels already with the 5Es. This is the first stage. Complications, creating something simple and then challenging it. Things like the predict, observe, explain. Get the students to predict what's going to happen in experience. Then you do the experiment and they observe it and then they explain why what they predicted either did or didn't happen. That kind of activity would be appropriate for the exploratory stage. The redescribing stage gets the students to challenge their existing conception. So again, they'll come in with naive conceptions, misconceptions, children's science, prior conceptions and so on. All of these terms. As I said, we usually use misconceptions. They'll come in with their misconceptions and they need to be able to challenge their existing concept and replace it with the scientific concept. That's essentially what we're trying to do. So the teacher will explain the scientific concept and how it works, how it's powerful, how the scientific concept explains their findings better than their existing misconceptions, if that makes sense. So this is the second and sort of middle stage, and you're actually getting them to understand the scientific concept in the first place and then apply it to being able to predict experience. It's like the, actually, you know, this is a bit like the conceptual change thing. So at the exploratory stage, you establish some dissatisfaction with their existing misconception. At the redescribing stage, you demonstrate that it's intelligible, plausible, and fruitful. So you are giving them the information and the evidence they need to decide to accept the scientific concept as an explanation for these phenomena. And then at the application stage, try out and extend it into new contexts and new kinds of puzzles. So they're doing some work with it. It's also a little bit like the create, test, use sequence, that once you've created and tested the concept, you can use it in a new context. You can apply it. You can expand to new contexts and new kinds of problems and so on. So you can see, I think I've mentioned now about 5 different frameworks for thinking about teaching altogether and similarities and differences. Now, I don't expect you to have the level of elaboration and complexity of your models that I have at this point, because I've been doing it for a while. But I hope you're seeing that these frameworks are all, in some sense, coherent, but they highlight different things. Otherwise, we could just find the one best and stick with it. But they bring our attention to different elements and ideas. And the final one that I want to talk about in this video is one that my colleague Xin Fan and I created around interactive simulations. And I'll be talking about interactive simulations more in the final week of the course. But we created this sequence for using interactive simulations are basically virtual, computer-based virtual labs. So rather than go to the lab and do an experiment, do it on the computer. And we talked about the affordances of that for learning. But we had a 0th step. We have, I think, 5 steps, but there's a step 0 first. And step 0 basically is saying, decide whether a computer-based virtual lab is the tool for the job. It may not be. If you want to do something with force and mass, for example, it might be better for the student to feel the force physically with a real object than to just see it represented on the computer. So is the technology the right tool, the information technology the right tool for teaching this concept? Make that judgment first. Don't just assume it and then go into your teaching sequence. The other point I would make is that this teaching sequence doesn't only work for interactive simulations. It works for anything, basically, because it's an approach to teaching science and it draws on conceptual change and so on. So once you're past step 0, once you've decided what technology, what teaching approach you're going to use, then in step 1, elicit and clarify the existing concept and the scientific concept. Now, this is a difference from the 5Es. The 5Es basically starts by going, let's have a bit of a mystery. Let's look at a question and so on. And then as we get through, it's like a mystery novel. You find out who the killer is at the end. In the 5Es, you find out the scientific concept, at least in the middle, and then you're sure by the end. in this approach, you do it differently. You say, all right, here are the candidate misconceptions. Here are the ways you guys in the class understand it. Some of those might be correct, some of those might not. And the teacher, if the scientific concept hasn't already come up, now it may, so the students may already know the scientific concept and talk about it. If they don't, then the teacher ideally also talks about the scientific concept and describes it and adds it to the mix. So you're not yet saying, this is the scientific concept, ignore all of your old misconceptions, because that doesn't work. That's just like propaganda. But you're saying, here's another way of thinking about it that you maybe haven't thought of yet. Second step, outline the predictions and implications of the existing concepts and the scientific concept. So you're being very explicit. In chemistry, I predict that when I put this litmus paper into this solution, it's going to turn blue or it's going to turn pink. And here are my grounds for saying so. And my theory says it's going to turn blue, your theory says it's going to turn pink. Now we can do the experiment. So at this stage, what you're doing is actually making it clear and explicit that a concept, a scientific concept, makes prediction possible about the world, and those predictions are testable. So, and you're making it explicit that if you hold this concept, then this is what you'll predict in this context. If you hold this concept, this is what you'll predict, and so on. Then step 3, testing it. So you do the experiment. In our case, we did it on the interactive virtual lab. In your case, you might do it in the real physical lab, but you test the concept against the real world, in the empirical test of evidence, and see which is supported and which isn't supported. And if you design the experiments well, then the scientific concept will be supported and the unscientific concepts, the misconceptions, will be unsupported. They'll make wrong predictions. And the fact that they make wrong predictions is what encourages the students to discard them and accept the scientific explanation as a replacement, if that makes sense. Step 4, once you've got that, you kind of make it really clear, nail it down and say, hey, guys, you get it, right? The scientific concept correctly predicted everything. The other misconceptions didn't correctly predict. In other words, they're not useful, they're not scientific, they're not testable, they don't meet the test of experience in the real world. So it's making it very explicit. And finally, the kind of the use step. Once they've got the concept, you work with them for a while to deepen their understanding, help them have a richer and broader understanding, and so on. We did this experiment, Xin did. She went back to Beijing and worked with students there and discovered that we got very large gains and effect sizes, really quite dramatic learning enhancements between the students who used our method and the students who used their normal method. So it works. This is a teaching sequence that has been empirically tested in practice and shown to work. So hopefully the comparing and contrasting of the 3 different networks frameworks that I talked about will be helpful in giving you a sense of what an instructional model looks like. As models are in the physical world. So the Bohr model of the atom is overly simple. It will explain some things for us. It's useful for some things, but if we want to do other things, we have to go to a quantum model that contains orbitals and subshells. I'm just trying to think of a good example from another, engineers are notorious for modeling real world problems like a falling cat using only cylinders, because cylinders are easier to do the maths on than cat-shaped objects. Now that's a model. It oversimplifies the real world to enable us to grapple with it, but it may be too simple for some purposes. A cylinder can't turn its weight the way a cat does so that it lands on its feet, for example. So these instructional models are models of what teaching is like. They're all inherently less complicated than the real world, because the real world is real complicated, but they help us to drive our attention to the important features. So something I kind of alluded to on the way forward, you can start at the middle, you can start at the beginning, you can start at the end, you can go forward and backward, step 2, step 3, step 2, step 3, and multiple times, and so on. Because again, these models were not etched on tables of stone by the finger of God on Mount Sinai and delivered by Moses. They are human constructions, they're heuristic devices, they're tools for thinking with. And so adapt them to your purposes, make professional judgments about them. And that's all I'm going to say about that. So hopefully useful in terms of thinking about the pedagogy that we use in senior science and what we're trying to do. What we're trying to do is get the concepts to be developed and elaborated and enriched in the students' minds and held deeply by them in working memory in a way that means that that's now how they understand the world. It's not, I was going to say it's not how they pass the exam. Yes, it's how they pass the exam, but it's how they pass the exam because it's now how they understand the world. It's now the tool that they use for thinking of and representing the world. All right.